cloud, we are studying young stars forming and turns out even lower mass objects. So the insets you see, I'll start with the top one first, are a brown dwarf. That's a demotivational poster to fail. Okay, it says fail up there. And the reason being that, as Linda pointed out to you, brown dwarfs do not have sufficient mass to ignite hydrogen fusion at their cores, so they never become self-luminous stars. So that's a brown dwarf. Another illustration here, also done, I think, by my former postdoc Robert Hirsch, shows what a free-floating planetary mass object might look like. And it's accurate in that it's not orbiting any star. It's just freely floating in the galaxy. And the final inset, all of these topics I'll touch on in the rest of the talk. The final inset is the first image from ALMA, which is the Atacama Large Millimeter Array up in Chile with 66 antennas now operating. But when this image was taken a few years ago, it was only about a dozen telescopes. And it's a disk that's imaged in its dust emission at millimeter wavelengths by the ALMA array. And you see that the size of that disk is just about 40 astronomical units in radius. And that is also embedded in this dark cloud in the background. So I'll go over my talk outline for you because since there's a lot of ground to cover, I thought it would be good to give you an outline. So first, so everyone's on the same page, we'll start with some definitions. And then I will give the historical context of how brown dwarfs were searched for historically. It's quite a long and involved story, I found out putting the talk together. And then I will tell you techniques that we're using to search for even lower mass objects, free-floating planetary mass objects. First, I'll outline one technique we tried called differential methane imaging, and then a new method we developed. And then I will show you on what basis we think there may actually be more planetary mass objects than stars in our galaxy, and how we're going to go about proving that. And to wrap up, I will show you some recent results from the ALMA array imaging disks around brown dwarfs and extrasolar planets. And finally, touch upon the possibility of life in these strange new worlds we're discovering. So, to begin, some definitions. So stars, I think I've just told this. Stars. Stars range in mass from about 8/100th of a solar mass, that's the little symbol for solar, up to maybe of order 150 solar masses. We don't actually know what the upper limit of a stellar mass is, but it's in that range. And stars shine by fusing hydrogen in their cores to emit light and heat and luminosity, and their luminosities are of order 1/1000th to a million of the sun's luminosity. And then we have the definition of a brown dwarf. Those range in mass from about 13 to 80 Jupiter masses. I switched units because those are nicer units for brown dwarfs. That's the symbol for Jupiter. And one Jupiter mass is of order 1/1000th of a solar mass. So brown dwarfs range from 13 to 80 Jupiter masses and are very, very dim. They're 1/100,000th of the luminosity of our sun. So just to give you some sense of scale for what 1/100,000th is, if you think of the size of the superdome And then you imagine the size of a little sweet pea. That's the ratio of 1, the sweet pea, to the size of the superdome, 100,000. So that's how faint a brown dwarf is relative to the luminosity of our sun. And then planetary mass objects are even fainter. They're by about that much of a factor again, 100,000. So only, I don't even know the word for 10 to the minus 10 solar luminosities. And their masses are of order 1 to 13 Jupiter masses. The delineation between the lowest mass brown dwarf and the highest mass planetary mass object of about 13 Jupiter masses has to do with the fact that deuterium can be fused into helium-3 at this boundary for solar composition material, and below that mass, there's no fusion of any sort whatsoever. And then I just wanted to say that the definition of a planet, okay, as of 2006, the International Astronomical Union decided that a planet is, first of all, orbits our sun. Secondly, is round in shape through its self-gravity. And thirdly, it has swept its orbit clean of debris. So that's why Pluto finally got demoted from being a planet, because it has not swept its orbit clean. So we have to call these objects planetary mass objects, not planets, for that reason. So just to give you relative sizes of these objects we're talking about, stars, there's our sun, there's a red dwarf star, which are the most numerous sort of star in our galaxy. And here are some brown dwarfs, one very recently discovered by an infrared satellite you'll hear more about, and there's Jupiter. So you see the sizes are similar, but the temperatures keep going way, way, way low. Okay, so I will tell you a little bit about the history of the search for substellar mass objects or brown dwarfs. This is where the searches have taken place, the techniques used, and kind of the history, what years. So the very first even theoretical idea that there might be such an object as a brown dwarf that isn't fusing hydrogen was made in the mid-60s by a theorist. And back then, of course, we had photographic plates, and so as research tools. So what people started to do was to look at the nearest stars within, tens of light years of us, and to look for motion, proper motions, little wiggles in their motions that might hint at an unseen companion that would have a mass of a brown dwarf. So those were the first searches. Then with the 1980s, we, in astronomy, made a huge leap in technology from the photographic plate to the charged coupled device, which is now ubiquitous. I mean, it's even in your cell phone for taking photos. And those were much more sensitive, so you could look at much fainter objects, and people started taking images of very young star clusters, since brown dwarfs are theorized to be much hotter when they're younger. So when you looked at young star clusters, the brown dwarfs in them would be much more luminous than they would be if you just looked in Earth's neighborhood. Then people started looking in the last decade or so for brown dwarfs close to us, not with this astrometry technique, but actually by direct detection, by cross-correlating colors of very faint objects from all sky surveys or very large surveys, such as 2MASS, which covered the whole sky in near-infrared wavelengths, the Sloan Digital Sky Survey, which covered a large portion of the sky in 5 filters, and then the more sensitive United Kingdom Infrared Deep Sky Survey, and then the WISE satellite, which was sensitive at mid-infrared wavelengths. All these are near or mid-infrared wavelengths because that's where brown dwarfs reach their peak of emission. And then an interesting technique, which actually that's why these gravitational lensing searches were begun, were to look for massive MA compact halo objects. Don't ask me what the OGLE and MOA are for, I don't recall. But basically, if brown dwarfs or, neutron stars or things like that could make up the dark matter or missing mass. And so they would look for gravitational lensing events towards our galactic bulge, with the background being the Large Magellanic Clouds. And finally, what we're doing with my colleagues is looking for these very low mass objects using large format near infrared arrays, which are really less than a decade old, and multi-object near infrared spectroscopy to follow up the very faint candidate objects we are finding. So first, the first search technique was to look for binary companions to known stars. And there's a picture of Jill Tarter from SETI Institute up here because she actually, in her PhD thesis, was the first one to coin the term brown dwarf. It turns out that not much was known about the atmospheric chemistry or physics of these objects back then, but if you looked at them with your naked eye, they would actually appear maroon as opposed to brown. And here's an artist's conception of brown dwarf and its star, red dwarf star, about 40 astronomical units away, whereas the actual first discovery of a brown dwarf, Gliese 229b, this is the brown dwarf, and that's the star. Okay, so the luminosity of this is just 7 millionths of a solar luminosity, and of order 100 or more objects were searched for close by objects to the Earth, using the Palomar 60-inch, and this was about the only one that was found. So they're pretty rare as companions to stars. The next search technique used CCDs to look for brown dwarfs in young star clusters such as the Pleiades, but even if you had candidate cluster members that were extremely faint and could be possibly very low mass, such as brown dwarfs, you still needed to confirm that they weren't just some background object. And some clever Spanish astronomers figured out that brown dwarfs, even when they're very young, would not have fused the lithium in their atmospheres that more massive stars would have fused and gotten rid of their lithium by the age of the Pleiades. So it took telescopes of the size of Keck really to get spectra of these faint objects to where you could detect the lithium absorption at 6,708 angstroms. So there are the lithium absorptions. So that proves that those 3 candidates, at least in the Pleiades, are bona fide brown dwarfs. Then the search for these in our solar neighborhood using the huge, large sky surveys I mentioned earlier. There's our galaxy from the 2MASS all-sky near-infrared survey. There are the Magellanic Clouds. So the near-infrared colors of those very faint objects were sometimes cross-correlated with optical photometry of the same objects, and that's how candidates were found for nearby brown dwarfs. Similarly, the same thing was done with there's the sky coverage of the Sloan Digital Sky Survey. Although it looked at the northern and southern galactic caps, nevertheless, stars that are really close to us are distributed uniformly around the Earth. So that was a great resource for finding newly discovered brown dwarfs. And then an even fainter near-infrared survey is carried out at the Ukurt up atop Mauna Kea, about 30 times fainter than the two-mass survey. And then the very successful Wide-Field Infrared Survey Explorer, that was a 2-year mission from 2009 to 11, and operated at 4 mid-infrared wavelengths, also discovered quite a few brown dwarfs. So the total count is of order 1,200 or so known today. And this shows you an image of our own solar neighborhood with the sun at the center. And in blue circles are previously known brown dwarfs in our solar neighborhood, meaning within 8 parsecs or of order 25 light years. And the red circles show all the very newly discovered brown dwarfs from this WISE satellite. So even as close as just tens of light years from our sun, there's this whole population of brown dwarfs that were just discovered a few years ago. That's how faint they are. And just to orient you, there are the Pleiades, and here's Orion's belt. Then I'm going to show you another technique, the gravitational lensing technique that is being used to discover actually even planetary mass objects, not just brown dwarfs. And this is a pretty amazing illustration, which I will explain to you of how gravitational lensing works, okay? So what you are seeing are actually 4 different galaxy clusters that are in collision. And you may or may not know already that the vast majority of baryonic matter, of what we are made up of, is actually in the intergalactic ionized gas, so in galaxy clusters. And the red emission is actually showing you X-rays coming from the colliding intragalactic intracluster gas associated with the 4 colliding galaxy clusters. The blue hazy image actually shows you the mass distribution of those clusters, and that mass distribution is actually calculated from computing what mass distribution would produce the lensed images of background galaxies by the dark matter of these 4 colliding clusters. So you can see that the dark matter is distributed very differently from the baryonic matter, and it was due to the lensed images, all these like long striated images of background galaxies, which were used to deduce, to infer the intervening matter distribution. So that's what that's the idea of how gravitational lensing can be used to infer intervening mass. So how is this used to detect brown dwarfs or planetary mass objects? Well, in these large surveys they had looking through the halo of our galaxy at the Large Magellanic Cloud, for instance. So if you have a light from a distant star, and you have an intervening, between us, an intervening brown dwarf or planet, as it passes between us and the background star, its gravitational field actually bends or focuses the light through gravitational lensing in such a way that as it passes in front of the background star, it makes the background star appear much, much brighter for a given amount of time. So this is an actual gravitational lensing event where the background star's light brightens, and then there's a little blip here on the side, which is due to lensing by a companion planet. And this is detected by many different telescopes. You see a Danish Perth, so they're all looking at the same object, and so they all detected this. So this is really a very low mass object that did this lensing. And here you see, so what happens is people just continuously take time series photometry of certain pieces of sky, and here you see a gravitational lensing event, and here you don't. So it came and went.
How do they know it's not a nova?
Because it has a very characteristic time signature, a shape with time. And it's, as you can tell, it's pretty, how do you say, symmetric in time. So you can see that was like a 40 days ingress and egress of this, the object passing between us and the background star. A nova has some other very distinct light curve. Okay, and now how we are looking for very low mass objects is within the nearest star-forming regions. And here are 3 examples. And the reason I'm using these 3 examples is because these are the first 3 star-forming clouds in which bona fide brown dwarfs were discovered. Rho-Oph, that's the young forming population of stars in it, is just 1 million years old at a distance of 125 parsecs. Taurus, which takes up a huge amount of real estate on the sky, also very young, but much more distributed young stars at 140 parsecs. And then the Orion Nebula cluster, very rich, also very young, but quite a bit further away, and therefore that much dimmer for its constituents. So why we're looking in the nearest star-forming regions is, of course, the closer a source is, the brighter it is. Why we're looking at the star-forming regions is because when brown dwarfs and planetary mass objects are quite young, this is a plot of luminosity versus age. I don't know if it's true to say, like humans, they're bright when they're young. That's not really true, because we get wiser as we get older, right? But anyway, brown dwarfs and planetary mass objects are quite bright when they're young, and then they just kind of fade with time. So you see different masses here of object. These are very low mass stars. With age, they will just even out in luminosity because they're fusing hydrogen, so they're putting out energy. But at below 80 Jupiter masses, in the brown dwarf regime, you have a slight initial period of deuterium fusion, but then again, nothing happens and they just fade with time. So those are some of the brown dwarfs discovered in these 3 in the Pleiades, and this one was the discovery brown dwarf in our solar neighborhood, Gliese 229b. So you see it's very old and faint. But when these are very young, so these are billions of years old, here 100 million years old. When they're just a few million years old, they're a factor of 1,000 to 100 brighter in the youngest star-forming regions than they will be if you just look in our solar neighborhood. So those are the reasons we're looking in star-forming regions. So at Rho-Oph, with large format near-infrared arrays on 4-meter class telescopes, we could actually detect, in theory, 2 Jupiter mass objects at the front of the cloud. Now, there's a caveat that in general, if you know the temperature of an object, so if you look in the field, let's look at 1500 Kelvin or 1400, you're not going to know the mass of that object, even if it's very low temperature, unless you know its age. And that's another reason to look at star-forming regions, is because we already know that they're coeval from, and we know their ages from the young stellar population that's already been studied. Whereas if you look at some random, very dim object in the field, brown dwarf, you don't know if it's 800 million years old or 5 billion years old, and therefore you don't know what its mass really is. So that's the other reason we look for young brown dwarfs and planetary mass objects in star-forming regions. And you see, we are sensitive to sources that are 13 Jupiter masses or less, even at 1 million years. Now, I marked that onset of methane absorption because that was our first try at finding young brown dwarfs and planetary mass objects in star-forming regions. Because it turns out, at least in field brown dwarfs, when you look at objects that are this cool, 1400 Kelvin or less, you start seeing a very characteristic spectral signature of methane absorption in the wavelength range about 1.6 microns in the infrared. So the first methane brown dwarf, which was the first brown dwarf discovered, that I showed you an image of a few slides back, Gliese 229b, this is its spectrum. And so this is the continuum here. There's water absorption, and here is around 1.6 microns, and then there's just a huge dip here, and that's due to methane absorption. That's a 900 Kelvin object. When you look at something that's slightly hotter, say 1800 Kelvin, you see that there is no stark methane absorption. Neither in this one that's hotter, 2500 Kelvin. So methane absorption sets in brown dwarfs at about 1.6 microns, and it's a very distinguishing feature, at least in field objects. So we thought, okay, why don't we just use some filters, use these huge new near-infrared arrays that we have available on 4-meter class telescopes, and integrate away and see if we can find objects such as this, which appear bright in the filter that passes the continuum, and basically the object disappears in the filter that passes the methane absorption wavelengths. So there's, for instance, a methane absorbing brown dwarf, and in fact, a lot of the original brown dwarf candidates from the big sky surveys were verified as brown dwarfs using this methane imaging technique. And this just shows you from 1.5 to 1.7 microns what the filters look like. There's the H band, and here's the short methane filter where there's an image of an object there, and there's the long methane filter, and then superposed are spectra of an object that's maybe 1800 Kelvin and one that's below 1400 Kelvin. So you see the cooler object has this methane absorption. So it's going to disappear in the methane filter, but it's there in the off methane feature. So okay, that was our strategy. And this is a strategy that was used by the Wide Field Infrared Survey Explorer telescope, the one that found about 30 brand new brown dwarfs within our solar neighborhood within 8 parsecs, only it was a mid-infrared instrument, and they used methane features at 3.4 on the methane feature and 4.6 microns off the methane feature, and they actually developed these two filters precisely for that purpose. So this shows you different temperature model atmospheres and where the two shortest WISE filters fall, and the methane feature is bright at 3.4 microns and then goes away. The absorption is present at the lowest temperatures. So all the field brown dwarfs discovered by WISE used this technique. It basically surveyed the entire sky in these filters. So we thought, well, why not do this from the ground with 4-meter class telescopes with larger near-infrared arrays, large format near-infrared arrays, because WISE only was a 0.4 meter and it integrated for 70 seconds per point. We had a 4-meter telescope and integrated for 15 minutes or 30 minutes per point. So we went to the few telescopes in the world that were of this aperture size and that also had these methane on-off filters. So here's the Anglo-Australia telescope, and there's our friend. You recognize the kangaroo there in the back? It turns out it's a nocturnal creature. I found out walking to the telescope. You hear these rustling in the bushes. Oh, yes. So that was Australia. And then we got some observing time on the 4-meter down in Chile at Cerro Tololo Observatory. And this was in August. As you know, that's winter in Chile. And lo and behold, we had snow. But it cleared up remarkably the few nights that we had, and we got some very beautiful data from an amazing imager they had there called New Firm, which also came up to the northern hemisphere, and we got to use it again at Kitt Peak. And then Palomar also has a large format near-infrared array with those two filters. So we got some beautiful data in the methane on-off filters and thought we found perhaps a few candidates in the row of dark cloud. This was the Australian data, maybe 22 candidates from 6,800 sources that were detected. But we need spectroscopic follow-up because there are ways that these may actually not have been true brown dwarfs. So we went to, they are such faint objects that you need basically the biggest telescopes around with very sensitive infrared spectrographs on them to follow these up to get spectra. So we went to fire on the Magellan telescope down in Las Campanas, and then also Keck. And here are the spectra of our two very best candidates, and as the poster here says, we failed. They turned out not to be methane absorbers. One of the objects, this one here, has a characteristic spectrum of the integrated light of a galaxy, and this is the spectrum of what an A star would look like, the integrated A stars in that galaxy, only it's shifted to a redshift of 3. So it looked to be like a methane absorber in our filters. Okay, and then this other object just turned out to be an active galactic nucleus. Well, we're not interested in those. So that's too bad. And, why aren't we finding these, okay? It was pretty upsetting. Because, here are some Keck spectra of there's a methane dwarf, okay? We know we can get spectra of them. And there's a hotter one, so there's no methane. There's a much cooler one, there's the methane. Well, it turns out that people very recently have obtained spectra, and this is pretty astonishing, of the planets that are orbiting this 3,260 million year old star called HR 8799. It has about 4 giant planets orbiting it. I mean, they've detected the orbital motion. Here, the central star is screened out. And they've actually managed to get spectra of these giant planets. Here is the furthest one, HR 8799b. Here is its spectrum. And I know you can't see too well from the back there, but there's no methane absorption, even though it has an effective temperature of 1100 Kelvin. So it's cool enough, but it has no methane absorption. And this is a result from 2011. So now a few more of these are being found, and people are wondering now, wait a minute, why don't we see methane absorption? And the theorists are realizing that, well, you could have in these very low surface gravity objects, because they're very young, so they're puffy, they're still contracting, different atmospheres where equilibrium hasn't been reached. You have mixing of the hotter layers from below, bringing up CO and destroying the methane, so you don't see methane. So, back to square one. How are we going to search for very young brown dwarfs and planetary mass objects if we don't have this technique of looking for the methane absorption? And so, taking a step back, how do we actually identify the young stellar content of a star-forming dark cloud anyway? And it turns out that you need very many different techniques, not just one. I guess it's just like keeping your health. You have to exercise, you have to eat well, you have to do a lot of things. It's not just one thing. So same thing with finding young stellar objects. You can look for optical variability, you can look for H-alpha emission, you can look for near-infrared variability, or disks that are display themselves as excess emission in the near or mid-infrared. You can look for evidence of associated jets, like here, an outflow activity, because very young stars spew out a lot of material when they're young. Or you can look for X-ray activity. It turns out that very young stars that don't have much of an accretion disk at all can be observed. They're much brighter in X-rays than main sequence stars, and they vary. So here's an illustration of 7 days of data of the Orion Nebula cluster taken with the X-ray observatory, the orbiting X-ray observatory, Chandra. Okay. We have to start you. So this is 7 days of data in just a few seconds. So if you see a very high amount of X-rays and this variable behavior, then you can be pretty sure that it's a young star and not some background one. Okay. Okay, however, it turns out that for objects such as brown dwarfs and planetary mass objects, those are too faint for pretty much most of these techniques. So we actually used some auxiliary data that we obtained during our methane imaging search and thought up a new method to try and identify these objects. So we turns out that we took near-infrared broadband photometry of all these fields to very faint limits, because remember, we're on a 4-meter telescope integrating 15 minutes. So we got to very faint limits, and we combined those data with the mid-infrared photometry from the Spitzer Space Telescope. And using the near-infrared data, we could infer the extinction to each source. And then we used some computer modeling to find given that derived extinction and this photometry, to find a best fit effective temperature and to figure out if these sources were in the cloud or background objects. So for the row of star-forming cloud, we separated our detected 6,800 objects into 3 groups. Those, most of them, which did not show infrared excess. Those which did show excess, those are objects with disk emission, pre-main sequence ones, and those that were on the border between the two. We could only really derive accurate extinctions for the non-excess and the disk excess sources, which were 80% of the population. And these are the results. We actually found a very large population of low mass objects, meaning brown dwarf or planetary mass, in the row of dark cloud, about 950 in fact. And the way this was derived was that there are different models that were fit to the photometry and the extinction. And for the excess sources, the non-excess sources, and these are off-cloud sources. And then these curves are what the main sequence at the distance to the cloud, that's where main sequence objects would lie. So sources that are behind the cloud that appear very faint would fall below the main sequence curve at the distance to the row of cloud. And that's where most of the objects in the off-cloud region we looked at fell. But for the excess sources, the ones with disks, they're all falling at very faint magnitudes, but above where the main sequence would be. And the diamonds there are spectroscopically confirmed brown dwarfs in the cloud from other people's studies. So this whole population, 80% of 950 objects that have disks and that are of the temperatures that at that age would make them brown dwarfs or planetary mass objects. And then here are a few that don't have disks. So we were pretty happy with that result. Yes?
On that slide, what's the y-axis?
That, very good question. Thank you for not letting me skip that. That's very important. That's the intrinsic brightness at 2 microns of each source. So that's how we know that's where the main sequence would be with no extinction. It would have that intrinsic brightness at that distance. Thank you for that question. So other workers in the field that were looking for similar objects would only use near-infrared wavelengths because, anyway, they maybe just use near-infrared wavelengths to try and find these brown dwarfs and planetary mass objects. And this is what their data would look like, or our data would look like too on such a plot. And here are masses. Here's a model track for such a young age cluster. This is 0.08, so that's of solar mass. That's about 80 Jupiter masses. That's where the brown dwarfs would start, all the way down to a few Jupiter masses. So that's what that line shows. And good luck trying to find what's what from such a plot. Whereas, so that's our data. But after we apply our extinction determinations for each object, lo and behold, we can separate out the objects that have no disk emission and the infrared excess with the disk emission. And this you can pretty much read off for the non-excess sources, the ones without disks, what their masses are, between 85 and 80 Jupiter masses. It's a little more complicated to figure out the masses of the disks, the ones with disks. You actually have to use the J-band photometry because disks emit in the K or 2.2 micron band. but not so much at 1.25 microns. So from those 950 sources, we discovered this is what their mass distribution looks like. This is the mass on this axis and the numbers in this axis. So as you see, going from, this is the brown dwarf limit, about 80 solar masses. That's a tenth of a solar mass. That's 1/100th of a solar mass. There's the boundary between brown dwarfs and planetary mass objects. So you see the number keeps going up as the mass goes down. So, of course, our fellow scientists are quite skeptical, and that's a few of them. And we have to prove that these objects are such low mass to them. And to do that requires tedious and difficult work of spectroscopy. And how are you going to get 950 spectra of such incredibly faint sources in the near infrared? You have to go to the Keck and to Subaru that have what are called multi-object spectrographs. So you can get near infrared spectra. This is a Moss fire on Keck of about 30 objects at once. There's 30 slits you can align on whatever source you'd like across. Or Subaru has this amazing instrument called FMOS that has 400 fibers. Each one can take a J and H band spectrum. So we are in the process of obtaining spectra. And what are we looking for? Since we know we're not finding methane in these, we're going to take this as our guide here. Here is Beta Pic, a nearby fairly young star, 10 to 20 million years old. And here's its little exoplanet. Little, well, it's 10 to 12 Jupiter masses. And here is its H-band spectrum. This was just acquired with an instrument called the Gemini Planetary Imager. And so they got an H-band spectrum, 1.6 microns, and this is what we're looking for, this triangular shape. Because it turns out that here's that triangular shape again. For objects that are of order brown dwarf masses or less, if they're very young, that means they have low surface gravity because they're puffed out. They have this sort of a triangular feature in the H-band, whereas for the same temperature, if you look at a field star at the same temperature, this is what its spectral shape is. So if it's a background star, it'll have that spectral shape, but if it's a very young, low-mass object, it will have that spectral shape. So that's the work we're currently in the process of doing for all those 950 sources. We don't have the answer yet, but we're working on it. So now I'm going to switch over to the final part of the talk, which has to do with imaging the disks around these objects with this amazing new instrument called ALMA. That's 66 millimeter, sub-millimeter telescopes working together as one. And here was the first brown dwarf disk imaged. The brown dwarf is 60 Jupiter masses, imaged in its dust emission at 850 microns. The disk is less than 40 astronomical units in diameter. And here is another brown dwarf, very young, that has a planetary mass object orbiting it as imaged by Hubble in H alpha. And we're going, anyway, I didn't get time to image this the first go around on cycle 0 with ALMA, but it's very worthwhile to do to see if that planetary mass object has a disk and what its mass is. These are the first few images available from ALMA now, 2014 publication of 3 more brown dwarf disks in Taurus. All of these are in Taurus. And what's interesting about these disks, these are the sizes of the synthesized beams that we're used to look at these, so that's kind of the resolution element. But the disks are slightly resolved. These are of order 4/10 of an arc second across, which is 28 astronomical units at the distance to Taurus. So all of these have radii of that order. They're barely resolved, but they are resolved. So it's interesting that they're that large. Because if these brown dwarfs were formed by ejection from a multiple system that's forming, you'd expect the disks to have been stripped and therefore to be quite a bit smaller. Now, how many of you have seen this ALMA result? Oh, good. A few in the audience have. Now, all of you have seen it. Because this really deserves to be seen by everyone. This is an absolutely stupendous image. The resolution element is 35 milliarc seconds, or 5 astronomical units at the source. It's 10 times better resolution than the previous images you saw of brown dwarf disks. And this actually is around a pre-main sequence star in the same Taurus molecular cloud called HL tau. It's one of the very brightest millimeter sources, so of course they're going to do a great job of imaging it. And what you see here are these evacuated rings in the dust disk. The whole thing is about 235 astronomical units across. That's huge. And the theory has been, and it's really just been models and theories, that if you have planets forming, they are going to clear their orbits of the material that they're accreting. And there you have, I mean, this is not just a model or an artist's rendition. This is the actual disk of this source. So it's quite spectacular. Planets forming already at 1 million years. Here's another ALMA result of the beta PIC disk. This is again from very recent, 2014. Now we're looking at carbon monoxide, which is a tracer gas for molecular hydrogen. Again, viewed with ALMA. This is a very, very large edge-on disk. There is beta PIC, and there's the planet. Beta PIC little b is the planet. And what's very strange is that they found this carbon monoxide distributed in these clumps. That shouldn't be there, because the UV radiation from the star would destroy this gas in just 100 years. So the idea is that the gas is being constantly replenished by comets crashing into each other and creating, the gas. So early solar systems are very chaotic places. You have things banging into each other. And finally, I'm going to sort of link this to thinking about new environments for life, because when you have, say, isolated planetary mass objects, as I said, 80% of the ones in Rove have disks. That means they could be forming moon systems. If you have moon systems, eventually you could have tidal interactions heating the interiors of the moon, such as we see in our own solar systems. So this is an image of Enceladus, a 300-mile diameter, less than the distance from here to LA, diameter moon around Saturn, and it is spewing, that's water ice. Okay, that's a Cassini mission image. And this ice or water ice geysers actually contain some silicate material, and that's building up one of the rings of Saturn called the E ring. And it turns out that the constituents of those grains have recently been analyzed, and they can be explained, their chemistry and their basically their chemistry and how they are produced can only be explained by them forming in hydrothermal vents at the bottom of the ocean. Oops, I went in the wrong direction. Yeah, the ocean from which this water is spewing out. So what do we see in hydrothermal vents? Near hydrothermal vents on our own planet, we see forms of life that no one ever suspected because there's no sunlight down there. The energy source is really from the heat and chemistry of the hydrothermal vents. So it kind of makes you wonder whether you could have such life evolving elsewhere in our solar system and perhaps elsewhere throughout our galaxy. Okay, that's it. Yes?
So there are lots of things in the universe that are much brighter and easier to see, and some people might find much more dramatic and interesting. What got you interested in these little things to start with?
It didn't quite work that way. I was working on star-forming regions, and it turned out that these are really good places to find such objects. So, yes.
So you talked about the low surface gravity around the Jupiter-sized
Yes.
object. And so I'm thinking, and there are indications that they're young.
Yes.
So
The two are kind of synonymous.
what I'm thinking is if you have an object the size of Jupiter and they have low gravity, it seems like the opposite. It must be
Surface gravity.
the surface gravity. So the surface must be very large.
Yeah, it's 10, yeah. It's larger when it's younger,
Okay.
and it gradually contracts to, what it will become in equilibrium later on. So it's hot, when it starts, it's hot, and larger, and then as it cools, it kind of shrinks, yeah. Yes?
I seem to recollect a long time ago that brown dwarfs contain a certain amount of lithium.
Yes,
Ordinarily destroyed in most stars.
that's absolutely right.
Because of their high temperatures, but present is brown dwarfs because of their low temperatures.
Correct.
Have you been able to assay or try to observe any some of these objects that you found?
Well, it turns out that the lithium line I'm familiar with is at 6,708 angstroms, and that's completely not, these are so faint that not even a chance. James Webb was a near infrared, so that'll be fantastic for these kinds of studies. In fact, I was going to ask my colleague Tom Green if he'd look at a couple of these, because he's got guaranteed time. Yeah. Yes.
By what mechanism is the PMO potentially be ejected from some early planetary system?
Yeah, so there is one colleague who had hypothesized that when you form stars, most of them are in binary systems. Most stars are in binary systems, so maybe at the very early formation stages, you might have several objects that are still forming, and they might become in very unstable, chaotic orbits, and some things might get ejected.
So there's still no fault of the PMO itself.
Right. Right. Yes.
It's hard to, for me to understand how a gravitational field of a free-floating planetary object would have enough to bend the light of some distant star. That's way in the background. But I understand
That happens if it has to do with how close the light comes to the background light comes to the object. So it's really right along, if it's really right along the line of sight. I mean, the brightening is not large, and it's a very short time. But it's just a chance if it passes right between us and the background star. Yes?
I've seen a scenario on TV where the possibility when the sun reaches the end of its life,
Mhm.
the Earth might be ejected